All right, we're going to be recording this. Let's see how we do. Okay. You can see all the way to here. Bad marker. That's nice. Which one in this room? It's this. Where's the other side of this thing? I can go out to here.
Yeah.
Can you guys see this okay?
Yeah.
I'm talking to the Zoom. I'm talking to the Zoom people. You guys can always move forward if you want to see. I'll try it right there so you can see it. No, I'm not seeing your chat, so let me look. All right. Somebody pipe in and tell me if you can see where it says Professor Lyon. Can you see that? I can't see the board. Yes. How about here? Can you see the board now?
The first one you wrote is just at the top of the video.
All right, so what we'll do is we'll keep everything below this line right here. There. So this will be the safe area for Zoom. How's that? Is that okay? Don't tell me. Somebody has to tell me.
The others are saying yes.
Good, okay. Sounds good. I'm not looking at the chat window, so I'll just listen for you guys. And if you have questions, interrupt me, because I'm not looking at the chat when I'm lecturing. Wow, this is exciting. They didn't build Zoom for the whiteboard. So welcome to an exciting hybrid Zoom computer architecture class. You're all supposed to be socially distancing now, which I guess you're doing, sort of. Do we have enough room for everybody to come in the class? There's like 32 people. I think if we have 32 people in this classroom, it will not be socially distanced sufficiently. So we're going to have to break the class up, and I'm sorry for that. It's, how do you say, university policy. It's policy. So we're being safe about it by socially distancing, and I guess that's the smart thing to do. So I can't, fault them for that, but I can't say I care for this this format. So, anyways, let me go through a little bit of the preliminaries for the course. My name is Professor Lyon. This course has a prerequisite, which is Digital Design 1, Computer Architecture, makes use of the material in that class. I have a syllabus which I put up online, and I've also put up an electronic version of the Patterson and Hennessy book, which is going to call an old edition, but it's free, and it's available for you to download onto your mobile devices for you to read at will. It's quite large, so you're actually better off with the electronic version anyways. Office hours, I've got 2 hours before this class, and I'll try and come to the class a little early, and I will certainly stay as late as I can, provided that another class isn't coming in after me. And I don't want to actually meet with a bunch of students in my office. So if you show up at my office, we're going to find a classroom that's empty and do the social distancing, because my office is too small to be socially distant. We can use the conference room in the School of Engineering. We can use any room available. And if you need to meet with me when you're not here on campus, or you don't want to come on campus, that's okay. I can zoom into your computer from wherever you are and wherever I am and try and help you in this way. So that's perfectly fine. I've got a syllabus that has a grading criteria. Sometimes students really care about grades. This is the grading thing. The midterm will count for a third, and it'll be open book, open notes, and done on Blackboard. Sometime around the 23rd of November, we are going to transition to a fully distant learning schedule, according to the academic schedule. So what that means to you, the student, is that your final will be done wherever it is you call home, in the dorms or really at home. And then it'll also be open book, open notes, and you're going to do it with Blackboard. It'll be done sometime around finals week. I'm going to give you 2 weeks to do it so that we don't have to deal with the registrar and their schedule. And you'll be able to do that with a couple of attempts. The same thing will happen with the midterm and with the homework. You get at least 2 attempts for each homework, sometimes more, depending on how difficult the homework is. And in general, it's going to be graded by computer unless there's a problem with the answer key, in which case I shall intervene and try and fix things. Hopefully there's no problems with the answer key at this point, because we've gone through it a few times, and maybe you guys will find other errors. I don't know. We'll figure it out as we go. So homeworks count for a third, midterm counts for a third, final counts for a third. I really like it when the students do the homework as they go. There'll be a weekly homework assignment. And what we'll do is we'll review in the class what you need to know in order to try and get through the homework. And in fact, what I will do is I will open the floor to you guys to prompt me to cover specific questions if they are the questions that are bothering you. And I will work those problems in the class. So it's more about knowing how to solve the problems than just knowing the answer. And so what I'll do is I'll teach you how to work the problem so that when you go to work the problem yourself, you'll see how it gets done and you'll learn a lot more that way. So that's my shtick for the syllabus. I didn't make paper copies for everybody because I put it online, and if I need to update it, I'll just update it electronically. But for now, I think that's it, unless you guys have some questions about the syllabus, about the course. No? So I like to open up the course with a basic question. What's the difference between a computer scientist and a computer engineer? Yes, sir.
Probably a computer engineer deals with more hardware of the computer than computer scientist, where does more programming and
Oh, computer engineers do a lot of programming.
yeah, but not as much hardware as like computer engineering.
Anybody? It's not bad. Anybody else have an idea? Yes.
Computer engineers are more focused on the lower level stuff and more interaction with the actual electronic components. And computer scientists are more of the theoretical aspect and the things that run on top of everything else.
It's interesting. Okay, I can see that. Anyone else? So I like to think that computer science is as much about computers as astronomy is about telescopes. If you want to build a telescope, don't go to an astronomer, go to an optical engineer. Astronomers do not build telescopes. They use telescopes to explore the heavens. You want to build a computer? Don't go to a computer scientist. Go to the computer engineer. They are the ones who focus on computer-based systems in and of themselves for their own end, whereas the computer scientists are using the computers to explore algorithms. So the essence of science is to explore what is, and the essence of engineering is to design what isn't. And so what we like to think of is that the computer engineer is skilled in the design of computer-based systems. Does a computer scientist need to know about computer hardware? Yes. Why is that? Because if you're going to write efficient programs, you better know something about the hardware upon which they run. If you want to build a compiler, you better know something about what a CPU is and the underlying architecture of the CPU. If you want to program anything involving, let's say, any hardware at all, you better know something about hardware. So it is the case that, yeah, one could make a compelling argument that perhaps it's more about hardware than it is about software, but the computer engineers definitely have to know a lot of software. And in fact, there's a lot of cross-pollination between the disciplines. So, having said that, what I would do with this rather large review, and this is a midterm that I borrowed from my digital design course. It basically goes through some of the elements of digital design, and what I would do is I would outline these things for you in sort of a rough way, a general way, not in a lot of detail. So we have topics, right? Such as, well, you know what I'll do is I'll put it over here. We have radix conversion. What's that? What's radix conversion? Uh-oh. This is the stuff this is review stuff, so you're always supposed to know it. Show of hands, who here has taken digital design? Uh-oh. Who was your professor? You. Me. Didn't we do radix conversion? You had this midterm. So what about base conversion? Remember base 8, base 2, binary, octal, hexadecimal, converting between them? That's
Yes.
radix conversion. You guys know this. Who did you have? That stupid professor who taught you nothing? Oh my gosh, that's terrible. Who was that person? So that was me. So then there's the Boolean laws. So there were these things we remember. Theorems. Oh my God, theorems. Postulates. Okay, I remember postulates. Axioms. Oh no, axioms. Things like and or, not, nor. Think back, way back. How long ago did you take digital design? Who took it last semester? Oh, so it was a long time ago. It was like last semester. For a long time ago. Yeah, it was pre-COVID, PC, before cable. So, yeah, so this is very good. We have these basic things that we worked on. Minimal forms, canonical sum of products, canonical product of sums, minimal sum of products, minimal product of sums. Got a question? Is that a question? Start you? So then we have, let's see, what other things did we learn? Gosh, we learned so much in digital design. It's really astounding. Oh my gosh, K-maps. Well, that goes with minimal product of sums and minimal sums of products. Let's see, what else did we do? This may, in fact, be a midterm that's very familiar to you because you probably saw this already. Don't cares, right? You guys remember the don't cares in your K-maps? Maybe you remember how to loop your K-maps. How about multiplexers? And what's the opposite of a multiplexer? Uh-oh. Demultiplexer, decoder. Decoder and encoder, multiplexer and demultiplexer. So you guys remember that stuff. I'm going through it real quick. I mean, this is like, 6 weeks worth of material. We're just going to review it in 1 week. So we're going to make sure you guys sort of, I don't know, remember something? Something about it? Okay. There's a blast from the past. It's a triode. So vacuum tubes. Tubes. So we had diodes, Sir Ambrose Fleming and the Fleming valve, the thermionic diode. And then we have solid state diodes with anodes and cathodes. There's a good one. LEDs. Light emitting diodes. That's very important, right? Because we had, this is the typical symbol for a diode, but it's also the symbol for a light emitting diode. And then you have a thing here called the anode and the cathode. And the anode, that's going to be your positive side, and the cathode will be your negative side. And if you look at your LED, you see you have a long and a short lead. And the long lead, that is called the anode, and that's your positive side. And the short lead, that's your cathode, that's the negative side. The LED is different from an incandescent light bulb in the sense that it can't be inverted and still work. That is, if you hook it up backwards, it doesn't work. Very important. So LEDs. What's the voltage drop across the typical silicon light emitting diode? Anybody remember? Yes.
Is it 0.7?
That's it. There you go. 0.7 of a volt. So you guys remembered stuff. That's great. We remembered stuff. Let's see now. Then there's this other question. How does one form a negative number using binary for fixed point numbers? I know, it was a long time ago. We're thinking like March, right? So couldn't have been something about sign and magnitude? Yes.
Yeah, so like the leading, like the first 0 or 1, and that would be like negative or positive.
Yeah, so we had a way to formulate these things. We did the complement and increment the accumulator, CIA, which stands for Culinary Institute of America. It's true. That's what it stands for. They're in Poughkeepsie, and they serve a very nice lunch, although probably not now because COVID. I don't know. Take out. So then we had adders and subtractors. And the adders were really, well, the subtractors were really just adders that used 2's complement. In other words, when you add a 2's complement number, you're forming its negative. And when you add a negative number to a positive number, it's just like subtraction, only somehow seemingly more complicated. So that's good. We got a few things out of the way here. All of this is being covered on this very short 46-page homework. 46 pages. What do we do? Then I got binary multiplication. And what else? Any other topics? NAND gates, OR gates. This is just the midterm, you know. You could have done the final. More theorems. Oh, De Morgan's theorem, you remember that. And that's it. 6 weeks. So here it is. 6 weeks of digital design compressed into 25 inches worth of whiteboard, or thereabouts. And that's homework 1. Whew, that was tiring. So, has anybody had a chance to look at homework 1? Yes, you did? Did you have any questions that you might like to ask about homework? No, it's all trivial. Trivial homework 1. Simple homework. Simple class, given by a simple professor, and that's it. So if I said, here's problem 1. 153 base 8 is equal to what number in base 10? How would I approach this problem? Yes. There you go. Positional notation. See this stuff stuck. You know what this is? This is learning. That's what this is, learning. Oh, I'm so excited. Okay, so it's going to be 3 times 8 to the 0 plus 5 times 8 to the 1 plus 1 times 8 to the 2. And then I think if somebody started by saying use a calculator, I'd say you don't need a calculator because you got one in here. But at the end of the day, you might like to. That'll probably be something like 8 times 8 is 64. And you can add it by without a calculator. It's not too hard. So that's probably chapters 1 through 5 of CATS. Who here needs a copy of CATS? You do? Well, it just so happens I'm using it now to hold up my iPad. So at the end of the class, I've got a copy here for you.
Resources that I asked you through the email about.
Yeah. That's good. I brought it in, and it turns out it's extraordinarily handy for reasons I didn't anticipate. Sorry about that.
Yeah,
I'm using it. If I move it now, my Zoom students are going to see, an earthquake. So that's no good. Let's see now. Is there any topic here that somebody might like to see an example of? And you Zoom folks can pipe in too. Add one to the front, somebody writes. I can see the board. Okay. I'm not exactly looking at the chats all the time, so if you want to pipe in, you can interrupt. It's okay.
Can we see something about the LEDs?
LED, sure. Let's do the following. Let's take the LED, hook it up to a resistor, and then what we'll do, this is the positive side, this is the negative side. We'll hook it up to a voltage supply, 5 volts, DC. And then This will be the positive side, and this will be the negative side. What we're going to do is put a current limiting resistor in series with the circuit, because we don't want to sink a lot of current into this LED or it'll get hot and blow out. So what we'll do is we'll put in a 220 ohm resistor. So now, how much current do you think this LED can sink at maximum? But let's use Ohm's law, shall we?
Yeah.
So this says E equals IR. And so what I'm going to say is E divided by R must be equal to I. But what is E? Is it 5 volts? Is it 7/10 of a volt, the voltage drop? I think E should be considered to be the difference between 5 volts and 7/10 of a volt. And if you subtract the two, you'll get 4.3 volts. Because this is going to drop by 7/10 of a volt right there. So if I go by 4.3 volts over,
That's because you're asking for the maximum, right?
yeah, the maximum.
So if you were asking for the minimum, would be like 5.7. Yeah. Is that 4.3?
5.7 volts, you mean?
If you were asking for the minimum.
No, I'm talking about current now. I want the current. So this is going to give me a number, which is probably something like 0.02, I'm guessing. So that's about 20 milliamps. You guys can, if you have a calculator, you can do that. What is this number? Anybody know? You guys have calculators on those laptops of yours? Well, I'm guessing it's something on the order of 0.02 or thereabouts.
Yeah.
Is that right?
0.0195.
0.019. Oh, that's 0.02. Yes. And so that's about equal, multiplied by 1,000, and I get 20 milliamps. Now that's a useful amount of current to light up a small LED. That'll light up and nice and bright. And the reason you,
I didn't get why we subtracted 4.7 from 5.
because there was a voltage drop. Voltage drop of
Is it always
0.7.
4.7?
No, but in the case of semiconductor barriers that are common, yes. You can find RF diodes, which have very low voltage drops, using different semiconductor materials, such as gallium arsenide. And in fact, you can also find gallium arsenide and gallium nitride being used in exotics, like the blue LEDs, in the Blu-ray lasers, and in other applications. So the answer is no. You can certainly find diodes that, for example, here's another one, the thermionic diode, the Ambrose-Fleming diode. The voltage drop can't really be known because we don't know the electromagnetic permeability between the anode and the cathode in a vacuum, because we don't know how good the vacuum is. So there are 2 different reasons why, we use 7/10 of a volt as a convenience. Put it that way. Also, the 20 milliamps is very good if you're trying to limit the amount of current that is being drawn from your microcomputer. Because if the microcomputer is driving the LED directly, it might not like taking 5 volts and running it straight to ground through a diode. In fact, if it sinks too much current, it can get hot and unhappy and start to blow out the ports. But for me, I get kind of sloppy about it, and I just throw the diodes on there for the Arduinos because those are robust enough to be able to take it and drive enough current, and then they stop. If you draw too much current, transistors get hot and unhappy, and they start to blow out. So people like to put in these current limiting resistors. And a lot of times what happens is if you're dealing with laser diodes, what you want to do is keep the voltage constant and vary the current. So you don't want to have a variable voltage supply that changes voltage. You want a variable voltage supply that changes current, because it's the amount of current that determines the brightness. It always wants to have the same voltage applied. And it's very easy to blow out those diodes. Let's see, what other topics can we cover? Nothing?
Can we run through like some dates?
Could you be more specific?
Something that has like the cathode and the anode.
The cathode and the anode?
Yeah.
Well, that would be this, right? Or,
Yeah.
or are you thinking about, you say gates, but then you say cathode and anode. You're thinking about something like tubes? Okay, we can do that. We can do that. Let's do the diode again, only this time with a difference. We'll do the thermionic valve. So for the thermionic valve, what we'll do is we'll put on a plate, which will be our anode. And then what we'll do is we'll have our cathode. And we'll use a cold cathode because we'll have a separate filament for boiling off our electrons. We will enclose the whole thing in a glass envelope. So now we've got a very sensitive diode with a voltage drop which we can't know. And this dates back from, what the date was? Must have been the 1800s, right? 1904 was the patent. And let's see, in 1908, DeForest added the grid. And the grid could modulate the voltage. With a small voltage, it could modulate a large voltage across the cathode and the anode. This is the moral equivalent of a field effect transistor, only not solid state. And as it happens, it is what you call a voltage variable resistor. Voltage variable resistor. As opposed to what we're used to when we deal with TTL or transistor logic in digital design, and we have a bipolar junction transistor, or BJT, which is a current-controlled current source. So one uses current into the base, there's the base. The other uses voltage into the grid. When you do this in a solid state system, you have a gate, a source, and a drain. This is the FET schematic symbol. This is the BJT schematic symbol. And this is the old style Audion tube. Can you build computers with old style tubes? So let me ask you this. Can you make a switch out of a tube to turn on and off the voltage that goes from the cathode to the plate? Yes, you can. If you build the tube so it does nothing but high-speed switching, they call it a thyrotron. And they had 18,000 of these in the original ENIAC computer, 1943. This is before they had transistors. And that was the original general purpose high-speed electronic computer. In that computer, the CPU didn't go into the computer. The CPU was a room, and you went into the CPU. Which kind of makes it cool, actually. So that's kind of a little bit of a rundown on in the midterm. You guys remember anything about multiplexers? You need a review on multiplexers?
Sure.
Yes? Let's do that. I'll grab one of the examples right out of the midterm. Well, right out of homework 1, actually. I like this. Okay. So the question reads, this is question 34, by the way. The pointy-haired manager got a deal on multiplexers, and he got a deal on 4-to-1 multiplexers. This is all he bought, 4-to-1 multiplexers. For the Gruntmaster 4000, you're required to build a 32-to-1 multiplexer. How many 4-to-1 multiplexers do you need to build a 32-to-1 multiplexer? So this is a question the Zoom folks can answer too. Just pipe in when you get the answer. Number 34. How do you approach this problem? I need 32 inputs. All I get is 4 inputs from a multiplexer. So what's the minimum number of multiplexers I need in the first row? Yes? 8, absolutely. So in other words, I'll have 8 4-to-1 multiplexers here. And that'll give me 32 inputs, but it's going to give me 8 outputs. Well, how many multiplexers will I need in the second row? Yeah. 2. Right? So then I need 2. And so then the 8 will feed into the 2 4-to-1s, and that's going to give me 2 outputs. Finally, I need a final row. How many do I need for the final row? Yes,
1.
just 1. You bet. And so 1 4-to-1 multiplexer will give me a grand total of 11, because 8 plus 2 is 10 plus 1 is 11, 4-to-1 multiplexers, just because the pointy-haired manager said, what a deal. We got these 4-to-1 multiplexers, but they were cheap. And you say, yeah, but you need a lot of them. And he'll say, yeah, but they were cheap. And your time is free. Yes.
Can I repeat that? Like,
Your time is free.
after the 8 4 or 8 4-to-1.
Oh, so let's think about this a little bit differently. Suppose I had a 4-to-1 multiplexer here, and another 4-to-1 multiplexer here. 1, 2, 3, 4, 1, 2, 3, 4. These gonna be 1. So now it looks to me like I've got 8 to 2. Now I put in another 4-to-1 multiplexer here, and another 4-to-1 multiplexer here. 1, 2, 3, 4, 1, 2, 3, 4. That now looks like 16 to 4, right? Because there's 16 inputs with 4 outputs. Now I get another 4-to-1 multiplexer over in here. That gives me 1 output. This is equivalent to a 16-to-1 multiplexer.
And we need to do that.
So now, if I get 2 of these, I'll have 32 to 2, and then I'll need another multiplexer on the output, and bang, I'm done. What do you think of that? Good, right? So now, if this were a 16-to-1 multiplexer, I would imagine that you would have 2 lines going in through here, and the same 2 lines wired in all the way through here, and then a line coming in here. This would be the most significant bit. A, B, C. That's how you would do the selectors.
So the answer would be 10.
That's a 16-to-1 one I drew. I didn't draw the 32-to-1 because it takes up too much space. But it's clear now. You can build a 16-to-1 multiplexer from 4-to-1 multiplexers using 5 4-to-1 multiplexers.
Yeah, for the 32, you need like 10 or 11.
11, right? That's just what we said. We had 8 in the first stage. That gave us 32. And then we had 8 outputs. So I had to have 2 4-to-1 multiplexers.
Let's, if we have 2 that, where we can get the 32 to 1, we will have 4 to 1, 2 of the 4 to 1, right? So that's 10 in total. And there we.
Yeah, but you got only 2 outputs here. You got to have 1 output.
Yeah,
So you have to add 1.
2 to 1.
Well, I added a 4-to-1. You only have 2 4-to-1 multiplexers.
So I can use the 4 to 1 as 2 to 1.
Sure. So that's that. Let's see now. What else do we need to know about multiplexers? I'll get another multiplexer question out of the homework. You know, what I like to do when I thumb through these things is I like to lick my fingers, but here in the new age of COVID, I dare not do it. So, straight from the big city, what are you going to do? This is problem number 23. Can you all see the board okay? Should I change to a darker color?
It looks fine.
Looks fine? Okay. So here's problem number 23. What we got here is an 8-to-1 multiplexer. Okay, 0, 1, 0, 1, 0, 1, 0, 1, 0. 0, 1, 0, 1, 0, 1, 0, 1. What is this? Here comes the output y, which is a function of x, y, and z. What is that function? Given the following, here, I'll write it in here. 8 to 1 mux. Given the following 8 to 1 mux. Find the function. Find the function. What could it be? Problem number 23. Find function. Find the function. Any ideas? Yes.
Z.
Z is exactly right. That's exactly right. Exactly right. How did you get that? Yeah.
Through a K-map.
Oh, K-map. Okay. Yeah, you could certainly do that. In fact, if you wanted to, you could write it as a truth table. Zero, 1, 0, 1, 0, 1, 0, 1. And if you looked at it, you could see right away by inspection, this is equal to Z. Or if you were really not sure, you could certainly write out the K-map. I have to erase this to do that, because I don't have enough space unless I go outside of the boundaries of what Zoom can digitize. I forgot how we did that. Did we use the most significant bit on the side? I think we went this way. We didn't do vertical K-maps last semester, did we? We did horizontal
Yeah, we did,
K-maps, right?
Yeah.
So I think we get it like this. This would be 1, 0, 0. So that would be the most significant bit, X, Y, Z, like that. That's how we did it last semester. And so now if you fill it in by numbering your truth table, then changing colors, one, 3, 7, 5. Now you can loop the whole thing, so that must be equal to Z. What do you think of that? Not good if the professor doesn't remember the K-maps. But there is another way to do K-maps. You can stand them up and you put them sideways. So I want to be consistent with what we did in class. Let's see. So that was number 23. Do you guys need to try a refresher in decoders? Yeah, decoder question? All right, so let's do question number 24. This is a 3 to 8 line decoder. with inverted outputs. And a NAND gate on legs 3 and 7. Find the function in minimal sum of products form. How would you find it in canonical sum of products form? Canonical sum of products form shorthand notation. What is it? 3 and 7 is right. I left off the end. That is exactly right. So now you can do the truth table. Right? Three, 7, and the rest are 0. I can do a K-map now. I'll erase this. Make a little room. And now, what's that K-map look like? I think that wrong. Shit. Isn't it? So now I'm going to put in lines 3, 7, loop them. And what's that equal to? Did I get that backwards? Was it supposed to be X, Y up here? Let's see, this is supposed to be 4. 1, 0, 0. Yeah, that's wrong. Just a minute. Just a minute. X, Y, Z. That's it. That's it. Label your K-maps properly. I did it right this time. So now it's got to be
So the function be YZ.
YZ, exactly. And that's the answer to question 24. So maybe it is good that we're reviewing this. I thought maybe I was boring you guys, but didn't get the answer right away. And also, I'm remembering how to label my K-maps. If I forget that stuff, you guys probably forget it too, right? Sure. So you got that. 3 to 8 decoder question. How about binary multiplication? Anybody want to see an example of that? Binary multiplication. So this is question number 31 from the midterm. And you know what I'll do is I'm not going to repeat the questions that I'm going over next time. We'll go over different questions. So if you want to, you know, I think you probably want to stay home and watch the Zoom presentation next time. It might be good because we'll try and cover different questions at that point. So I said it was going to be the same class both times, but it kind of doesn't make sense because people will have different questions then, and you guys will be able to pipe in with different questions too remotely. So that actually makes it better if I go through different questions. No sense going through exactly the same questions. You might as well just watch the recording. So let's, because it's a big homework, right? And you want to get through as many questions as you can. So it's actually, I think it's more helpful if I do 2 separate sessions that are going to cover more material than just the same material. It doesn't make sense. So, so you folks out there in Zoom land, you have to come with questions on Monday. And you folks here in the classroom, you're going to have your questions asked remotely. And don't be shy about piping in with the microphone because I may not be paying attention to the chat facility.
On Tuesday?
Do we meet Tuesday? I thought we were Monday, Thursday. Aren't we meeting Monday? Oh,
Tuesday's a Monday.
Tuesday is a Monday because Labor Day. So yes, I will see you on Tuesday. That's right. This Tuesday is Monday. That doesn't sound at all confusing. Tuesday is Monday. What is it talking about? So let's see. 101 times 1011. We're going to multiply. Base 2 multiplication. We have time, right? This thing ends at 3:15, does it? We have time? We have time. Yeah, we have time. Yeah, let's do it. So, it's this way. 1 times all of that. 1 times all of that again. 0 times everything. And then 1 times all of that. So in a sense, it's just like long multiplication with a difference. And the difference, you got to do this addition here. 1 plus 1 is equal to 1 carry, 0 carry the 1 plus 1. And then that's 0 carry the 1. And that's 0 carry the 1. And then that's 0 carry the 1. I got it right. That's good. That's good. So that's the answer to question 31, in case you're wondering. Binary multiplication. So it's coming back to you now, right? So we're skipping around from topic to topic, doing an example on each, but the fact is, when you see it, you understand it right away. You're getting it. You've seen it before. And this, you know, this has value because what it's doing is it's kind of taking the learn forget cycle and short-circuiting it and putting, you know, that stuff you saw before into long-term memory. It's coming back to you because you're refreshing it. So having these kinds of reviews, I think it's very valuable. Right? keep in mind, this took us like 6 weeks to get through 5 chapters just in this one homework. Let's do a different homework assignment here. Let's try a different question. Okay, does anybody remember, this is question number 37. Does anybody remember what a ring oscillator is?
So 37 or 27?
Question 37. Ring oscillator. See you later, oscillator. A ring oscillator. I can call the operator on my little ringing oscillator. So, what is that? What is a ring oscillator? Yes.
I forget what kind of specific gate, there was like an odd number of a certain gate.
Yeah, that is exactly right. So here's an example. This is our first feedback circuit. Just 3 inverters. That's a free running oscillator. It is temperature sensitive. It is sensitive also to the delay in the gates. And it can be fabricated using anything that can form an inverter. So for example, if you have, oops. Three NAND gates in a row. It's also a ring oscillator. How do you make it stable? That is to say, how do you make it so it is relatively temperature insensitive? Suppose you wanted to use it as a clock, and you wanted a stable clock that you could use for your circuits, your switching circuits. How would you get a stable square wave out of the ring oscillator? Any ideas? Well, if it was me, I would add a crystal. A little crystal is actually shaped like a tuning fork made out of quartz, and they have these things in places like this watch. The Timex watch is probably as accurate as any quartz-controlled movement. And the reason why is because it has a stable oscillator, a crystal oscillator, quartz oscillator, that operates at 32,768 hertz. It then gets divided down until you get 1 pulse per second. That drives an efficient stepper motor, which actually causes the movement of the second hand to sweep across the face of the dial. Now, granted, there are other complications that make a watch more expensive. For example, this one has the date, but the date is always wrong, but it doesn't matter because I can't see it anyway, so I don't bother with it. It also has other complications. You can push the crown in and it glows in the dark, but I never use that either. But in any case, sometimes you can get them so that they're, gold encrusted with diamonds and all these other things. And then they have these things they call joules, 17 joules, 18 joules. And what that does is it gives you a ruby that actually serves as a pivot inside of the movement. and that's supposed to reduce the friction. But the way I deal with it is I crap up the watch and then I throw it away and then I buy another one. So I don't care. It's just a way to tell time. And I get hard. I'm hard on watches. I bang them up and I scratch them. I do have good watches. I just don't wear them normally. So this is a thing, a ring oscillator. You need this for your timing, right? You need a way in which to keep time for synchronous circuits and keep them stable. And you can build this with a simulator, and it'll work, you know, in Cortis or whatever simulator you like. Let's see, what else do we need to do? I don't know. It might be torture, but did you want to see De Morgan's theorem again? Yes? I'm hearing a yes? Yeah. Yes? Okay. He said to me, no, not De Morgan's theorem, oh my God. And I'd say, okay, we won't do it. So, what's that equal to? You guys know this. I thought you knew this. You know this. Yes.
Not A plus B.
Yes, there you go. You know this. Of course you know this. I don't know. You know. Right? Everybody good with this? De Morgan's theorem. Let's do so this is going to be problem number 49. Problem 49. What's this equal to?
Not A times not B.
That's it. De Morgan's theorem. De Morgan's theorem. Let's see if there's anything else we need to do here. Let's do time problem number 7. Problem 7 says AB or ABC prime equals using, don't use, you know, K-maps when you see something this simple. Okay, just waste your time. You can do it with K-maps. There's no doubt. Yes. A, that's the answer. And so what do we do? Well, we factor out A and write B or BC. Then we factor out B, and we get B times 1 or C. And then we see 1 or C is equal to 1. Oh, you could factor out AB. Factor out AB multiplied by 1 or C. Is that right? Oh, wait. This has to be simplified. I simplified it incorrectly. Sorry about that. Ah. Now we're on AB or AB prime or AC prime. It's A times B or B prime or C prime. B or B prime is equal to 1, 1 over C prime is going to be 1, and so then the answer is A. That works out good. That was question 7. Okay, you guys, you asked me a question. All right. How about a product of sums question? Shall we do one of those? Yes.
With the canonical expressions, what is the difference between a capital M and the lowercase m?
Max term and min term. So the question was, what's the difference? I'm repeating it for the sake of the Zoom folks. Question was, what's the difference between capital M and little m? And that's the difference between max terms and min terms. So if you have capital M, it's got a pi product next to it. And if you've got little m, it's got a sigma for summation versus multiplication. So let's assume for the moment that you are interested in obtaining a minimum product of sums given a K-map. So here is your K-map. Actually, now that I look at it, that numbering scheme doesn't work, does it? Right? Because this is going to be 1, 0, 0, that's 0. This looks to me like it's going to be 4. Over in here, it's going to be 0, 1, 0, so that would be 2. See, when you do it like this, you get weird results, don't you? Don't you? That's what it says. That's what they get here. 1, 1, 1, 0, 0, 0, 1, 0. That's what's given. And then it says find the minimum product of sums. Well, if I was going to find f prime, I would loop the zeros. If I loop the zeros, what do I get? Well, let's see. I could loop here, and I would call that B A, AB. I could loop over here, and I would call it BC prime. I could loop over, pick another color. This really isn't another color, it's just another marker. I'll loop this way, and I'll call it AC prime. So now F prime must be equal to AC prime or AB or BC prime. What's the minimum product of sums? What should I do now? Oh, I have to look up to the heavens and ask Augustus de Morgan for help. Help us, de Morgan.
You simplify it.
Yes, his theorem, thank you, has come to the rescue from the grave. So that F must be equal to A prime or C, or A prime or B. Just a minute, that's a multiply. That's a multiply. All right, or B prime or C. And B prime or C. And let's see. That was question number 17.
For the middle, it would be A prime or B prime.
Yeah, let's just make sure I got it right. That should be A
When you
prime
wrote
or
the,
B prime.
yeah.
There it goes. There it goes. It should be B, C, sorry, B prime C. That's right. And then there, this one should be A prime or C. There we go. That's it. Thank you. So the Zoom folks were heard from. That was good. So that is, I'm just checking it for correctness. That is correct. It's not in the exact same order, but that is the answer to 17. So that's how you do that. And it is 3:14. Are there any questions? You Zoom folks got any questions? So remember, Tuesday is Monday, and so we'll see you Tuesday. And if that's it for the questions, then I thank you. Stay safe and enjoy the weekend. Thank you.
Have a good one, Professor.
Thank you. You too. Bye-bye.
Thank you.
Change the disconnect audio. How do you stop the recording here? Stop.